We continue with section 6.1 on complex numbers, and we are looking at algebraic operations of complex numbers. So let's look at remark 6.1.6. It says, if you're given two complex numbers z and w, then the difference of z and w is the complex number z minus w, which is equal to z plus then the additive inverse of w. And then if n is a positive integer, we denote by z to the n the complex number obtained by multiplying z by itself n times. So for instance, z cubed will be equal to z times z times z. So you'd start by doing z times z, and you get a complex number, and then you repeat that again to get z cubed, right? And let's look at the next remark, remark 6.1.7. So we associate with every real number a the complex number a not 0. Sorry, a0. So what does that mean? That means that if you for you to represent a real number a as a complex number, you can represent it as a naught. So if a and b are real numbers, then adding them would give us a naught plus b naught. We just add the respective real parts and imaginary parts, and then we get a plus b naught, which is consistent with what we know, that if you add two real numbers, you get their sum, which is a plus b, and then the naught there is just well, it would agree with this association that we did in the first place. And then if we multiply, we are expecting to get ab naught, right? If we are looking at this, so if you do the multiplication of these two complex numbers, and then we apply the rule, we will see that we will get ab naught, which is consistent with that. So we may therefore think of the real numbers as a substitution of the complex numbers. We call a complex number z real if its imaginary part is equal to 0. That is, if z is that is, z is real if z is equal to a naught for some real number a. The usual algebraic operations on real numbers agree with the algebraic operations on complex numbers, like what we have just noted here, when applied to real numbers. So we therefore make no distinction between a real number and a complex number a naught. In particular, we denote the complex number not by 0 and call it 0. So that is that. And let's look at the next remarks, remark 6.1.8. Consider the complex numbers 1, 0, and one that we are going to call I, which is equal to 0, 1. Then every complex number z is equal to ab, which is equal to ab, can be written as z, which is equal to a naught plus 0b, which is going to be equal to a naught plus b naught times I. So if you think of this I as 0, 1, and then you multiply that I, this 0, 1 by b 0, you should be able to get 0b if you apply the rule for multiplication of two complex numbers. Now, since we identify the real numbers a and b with complex numbers a naught and b naught, we adopt the notation z is equal to a plus bi, right, for the complex number z, which is equal to a bi. This is known as the standard form of a complex number. So this is what we are used to, but it really comes from this fact, right? And if the imaginary part of a complex number z, which is equal to a plus bi, is negative, we write z to be equal to a minus bi instead of z equal to a plus bi. For example, the complex number z, which is equal to 2 plus minus 3i, is written as z is equal to 2 minus 3i, right? And number 3, if a complex number z is which is equal to a plus bi is real, that is its imaginary part, which is equal to b, is 0, it is acceptable to write z to be equal to a instead of z is equal to 0i. Likewise, if the real part is 0, we can write z as just equal to bi instead of writing it as z which is equal to 0 plus bi. Now, in standard form, the expressions defining addition and multiplication take the form. So if we do z plus w, we then add the real parts and then the imaginary parts with an I, and then if we do the product, then we get AC minus BD plus I AD plus BC for complex numbers Z, which is equal to AIB, and W, which is equal to C plus BI, right? And then we also know that I squared is minus 1, and we can do the calculation. I is equal to 0 1 0 1, and then if we apply the rule for complex multiplication, we get minus 1 0, and we know that minus 1 0 can be thought of as minus 1. So as a motivation for the definition of multiplication, consider the following calculation. So if you have for complex numbers, z equals to a plus bi, and w equals to c plus di. If we do the multiplication, we can see that that becomes a plus bi times that, and then if we do the expansion here, we get that, which is equal to that, and then here we use this fact that I squared is equal to minus 1, and so therefore this becomes minus BD. So we have AC minus BD, and then if we take coefficients of I, we get AD plus BC times I outside, like that. And this is consistent with what we already know, so therefore this works, right? Let's look at example 6.1.9. So we are given z equals to 2 plus 3i, and w equals to minus z plus I, and y equals to 2 minus 4i. So we can do the simple calculations. Zw minus y squared, we can just multiply these two, use the rules that we know, and we get that. Same applies to this. We can put our z and then multiply everything. There is 2w, which gives us minus 14 plus 2i, and we just do the calculations and get that, right? Let's look at theorem 6.1.10. So for every non-zero complex number, z which is equal to aib, there exists a unique complex number z to the minus 1 such that z times z inverse should give us 1. So that one is not, there's something missing there, right? So let's look at the proof. So let a be let z be equal to a plus bi, be a fixed non-zero complex number. Now for any complex number w, which is x plus yi, zw we know it's going to look like that. And then by the definition of equality of complex numbers, which is definition 6.1.2, zw will be equal to 1, which can be written as 1 plus 0i if and only if the real part, which is ax minus by, is equal to 1, and then the imaginary part, which is bx plus ay, is equal to 0. Now we express this system of equations in the form ax plus b. This is a system of equations, so we use what we already know, and we can see that zw is equal to 1 if and only if ax is equal to b. Now we also know that the determinant of A, of this matrix A, is actually a squared minus b squared, which is a squared plus b squared, right? And because we chose our z not to be equal to 0, at least one of, it means that at least one of a and b is a non-zero real number. And because we are adding, so we know that a squared plus b squared is going to be greater or equal to 0, but we also know that one of these is non-zero, so therefore the determinant has to be greater than 0. And then we know from theorem 2.5.25 that this implies that if the determinant is greater than 0, then this system has a unique solution. And it now follows from 6.1, there exists a unique z, because we get a unique solution, so therefore it means there exists a unique complex number w, which is what we are calling the inverse of z, such that z times z inverse is equal to 1. Right, so that is that for that proof. Let's look at definition 6.1.11. The conjugate of a complex number z is equal to a plus bi, the conjugate of a complex number which is equal to a plus bi is the complex number z equals to, there's supposed to be a bar here on top, which is equal to a plus bi, right? So this is a complex number related to z. Let's see, and we have some properties of conjugate complex numbers, right? So let z and w be complex numbers, then the following are true. If we take the conjugate of z plus w, it is just equal to the conjugate of z plus the conjugate of w. And if we take the product of z, the conjugate of the product of z and w, it is just going to be equal to the conjugate of z times the conjugate of w. And also z times its conjugate is a real number, and in fact the real number is a squared plus b squared. And then the fourth property is that the conjugate of a conjugate of a complex number z is the complex number z. So we are going to do the proof of the first one, and then the rest are left as exercises, and that is exercise 6.1, number 7 in the textbook. So let z be a plus bi and w be c plus di. Then this means that if we add z and w, we get a plus c plus b plus di. And so that if we take the conjugate of this, then we get a plus c plus minus b minus d times I. But since the conjugate of z is a plus minus bi and the conjugate of w is c plus minus di, we have that if we add these two, z plus the conjugate of z plus the conjugate of w, which are these, if we add them, we will get a plus minus bi plus c plus minus di, and then if we take the real parts and the imaginary parts, we get something like that. But this is just equal to what we have calculated on top there, which is the conjugate of z plus w. And so therefore our statement 1 is true. Right, then we have got another property, and this is theorem 6.1.13 in the textbook, and it says let z be a non-zero complex number, then its inverse is equal to 1 over this number, which is z times its conjugate times the conjugate of z. So we've got a formula of how to get the inverse of z using its conjugate. So let z be equal to a plus bi. Then theorem 6.1.12 part 3 tells us that the complex number z times z squared, z times its conjugate is equal to a squared plus b squared, which is a real number. And since the conjugate of z is non-zero, either a or b is going to be a non-zero real number. So therefore what it means is if we take z and times its conjugate, which is a squared plus b squared, because one of them is not equal to 0, it means even this value is not going to be equal to 0. So let w be this complex number that we get. Then what it means is w is equal to, so if we take that, so we know that this is 1 over a squared plus b squared, and then we know that the conjugate of z will be a minus b. So if we do a bit of calculation, we'll see that w will be equal to a over a squared plus b squared minus b over a squared plus b squared I. And if we multiply, so what we want is to check that this w is, if it gives us 1 when you multiply it with z, then it means that w is indeed the inverse of z, right? So if we do z times w, then we do the expansion, we get that using the definition of product of a product of two complex numbers. And then if we do, so on top there we get a squared over a squared plus b squared over a squared plus b squared plus, and then inside there we get minus ab and then plus ab there. So if we add these two, we get that this becomes a squared plus b squared over a squared plus b squared, which is equal to 1. And then this becomes 0 because that one is just the negative of that, and so we are left with 1 plus 0i, which is equal to 1. And from there that means that the multiplicative inverse of z is equal to 1 over this real number times the conjugate of z. And let's now look at definition 6.1.14 in the textbook, and it talks about dividing two complex numbers. So suppose that we have got z and w which are complex numbers, and w is not equal to 0, so it's a non-zero complex number. Then what it means is z over w is just z times the inverse of w, right? And the reason why we put this is so that we are able to say z over w, otherwise we can't get its inverse, right? So let's look at the example that we have. So we write the complex numbers zy plus y squared over w in a standard form, where z is equal to 2 plus I, w is equal to that, and y is equal to that. And what we want to write it, we want to write it in the standard form, so we want it to write it in the form of a plus bi. So according to definition 6.1.14, it means that for us to get this, we have to whatever is at the bottom, we have to multiply by the inverse, right? So we get zy plus y squared times the inverse of w. And so if we do that, so we can find zy plus y squared, we just do multiplication, and then we get minus 6 plus 4i. And for us to find the inverse of w, we use what we got in theorem 6.1.13, and we are able to find it as that. And so therefore, if we do the multiplication of zy over y squared times the inverse of w, then we get that, which is equal to minus 9 over 5 and minus 7 over 5i. And so that is that. So that's how we use the definition 6.1.14. Right. So lastly, we look at a remark, and it says, using the multiplicative inverse of a non-zero complex number, we can define negative integer powers of complex numbers. And if z is a complex number that is non-zero and n is a positive integer, then z to the minus n becomes the inverse of z to the power n. And so what it simply means is, if you want to find this, then you start by finding the inverse of z, and then once you find the inverse of z, you can multiply that inverse n times to get z to the minus n. So if we think of it, so if we are given z, which is equal to 2 plus I, then we know that z to the minus 2 is going to be equal to z to the minus 1 squared. And so we start by finding the inverse of z, which we can employ theorem 6.1.13, that one here, to find the inverse first, and from there we can then multiply, we can do multiplication of z inverse by itself, and then we get that. So that's how we can then work with negative integer powers of complex numbers. That is all for section 6.1. Thank you.